So I'm here to present to you a build system. Oh, some feedback there. Called Tundra. And my name is Andreas Fredriksson, or Dep of TBL. So about me. Hi. I think it's on. Do I need to? Okay. So I've been programming for a while. Last 10 years I've been in the game industry, hacking on games such as Battlefield and the Frostbite engine. And you could say I'm a demo scene hangaround nowadays, but I used to be in the demo scene. So now mostly I'm doing tools, and what we're going to talk about today is one of those tools, I guess. We also have a pretty cool Amiga remote launcher on Aminet you can actually download. So that's one of the other tools I put out. So, well, it's easy to get sucked into the demo scene if you're DICE because, well. So, I mean, why do we need another build system, right? There's plenty to choose from. Well, if you look at them, you'll find there's a bunch of limitations in them. And over the years, these grew on me too much. And if you look at these really quickly, Make, everyone knows Make, right? It's whenever you start to set up complex dependencies between stuff, it usually falls down, and you really can't make it cross-platform, or you can't express what you need. So it's pretty primitive. Jam, on the other hand, is pretty unreliable if you want to do code generation and more complex builds, which we'll get into later. And also SCons, if you ever tried that. It does everything beautifully on paper, but it's so slow that on some projects, it's faster to just nuke everything and rebuild it from scratch than to let SCons do the dependency checking. It's a joke. And Visual Studio, obviously, is another candidate, but it only works on Windows. And, you know, you get the same story over and over again, and for me, as a native code developer, what I want to do is I want to iterate on code. I don't want to put up with this bullshit. So, what's this then? It's actually a pun on the Frostbite engine at DICE. It's a great way to get Frostbite. Yeah, it's a bit far-fetched, but apparently there are some Tundras where it's really cold. So, this is my attempt to fix some of these issues, if you will. Some specs on it. It's getting to 1.0. It's not something you'd polish and put in a box. Far from it. But it's usable. It's getting there. You can run it on anything, which I think is important. And it's a traditional command line tool. So the thing we're going to talk about later is how it separates configuration and build engine. So it has a flexible configuration layer, but then a high-performance build engine. And they basically just talk to each other once. And you can just get the source. So I'm going to give you the demo coder's sales pitch for this. This is a great tool for demo coding because you can mix tool sets. So if you want to, put in crazy like PS2 tools or Amiga tools, you want to run your NES compilers, it can do it. It's really easy to add tools. So, well, that's one of the real big strengths. Also, the thing I really wanted to make right with this tool is incremental build times. Because when we're coding, we want to see the changes instantly on the screen, right? We don't want to wait for, if every incremental build takes you a second of dependency scanning, that pisses you off. So that's what pissed me off. So what I want to do is I want to use multi-threading everywhere. So Tundra is multi-threaded. Basically, everyone has, even these laptops have 4 or more cores, right? So why not use them for dependency scanning? And the final thing is, if you ever want to create custom code, read some data file and produce some C code at build time, that can usually be tricky, and you usually don't want to do it. With Tundra, it's really easy to do. So I'll show you. So I set out to do this thing, and I had a few design philosophies. It should be simple and fast, because simple is fast, usually. You should just build code, stay out of your way. And some build systems, that can't really be said about them. They want to take, they take center stage, and they want to, you have to keep feeding them. And utilize the multicore hardware, obviously, as we talked about. And separate configuration from building, because in some build systems, you can't really figure out where the build system begins and the script ends, or vice versa. You can sometimes find that you're running scripts when you should really be executing commands and stuff. SCons is one example where you can write everything in Python, but then it's also glacially slow, right? So my design philosophy was to do the config up front once in Lua, and then just have a high-speed build engine that doesn't use any scripts. So we'll see a little more later about that. So I also had some non-goals, which are equally important, I think, when you set out to make something, a piece of software. There should be no auto-configuration or guessing, because, so what I mean by auto-configuration is basically if you ever run configure or make or something like that when you're downloading a piece of Unix software. It may be great if you're targeting 25 platforms with this piece of technology, but we rarely do, right? We want to target our PC config, or Amiga config, or 360 or PS3 configs if we're doing game development. We don't want to target everything, and we certainly don't. I mean, porting your software to a new hardware platform is an undertaking that can take weeks, right? Making the build system find the right compiler tool is the biggest challenge you're going to have. So, and this is where I think most build systems, they start with good intentions, but then lead you astray, and they go searching for tools, and they do it every startup. Every time you start the build system, it's go scanning for tools. I know what my tools are. I change them once every third year, right? So that was one of the design goals too. Just make it explicit and get better performance. And also I didn't want a general purpose tool that could, do your laundry, do a bunch of HTTP requests, talk to your version control server, a bunch of that bullshit, because frankly, does anyone use those things anyway? So focus on one thing and try to do it well. And you can also do .NET with this if you really, really want to. So I'm going to briefly go through the config layer if you're going to use this tool. So as I mentioned, I want to separate the front end from the build engine. So the reason why I want to do this is, well, C is a pretty crappy language to expose configuration details in, right? Not to mention you have to rebuild it all the time and stuff. So Lua is a pretty good fit for this because, well, it's tiny. It sort of lends itself well to configuration. So I'll show some examples later. So basically, these are the activities that are separated in Tundra internally. So all the command line front end stuff and making a DAG, directed acyclic graph, all that stuff is in the Lua part. And then there's a build engine, and you can see the relationships and sizes. Right? So that's I think one of the new or sort of interesting choices about this. So when you're going to configure something with this, there are two files usually you worry about. The first one is called tundra.lua, which is where you set up your global stuff. So you have a bunch of tool sets, and you want to target. Well, if it's a simple project, you just have one, right? You pick your GCC for OS X, or maybe you have Visual Studio for Windows. So you set that up, you set up your global settings, and then you tell the build system where you want to pull your DAG data from. So this is usually called units.lua. It doesn't have to be, but it usually contains the build units, that is your libraries, programs, and so on. So that file is actually what defines the DAG for the build system. So in there, you'll not only have the build products, but you'll have some fine level tweaking too. Maybe defines, you want to disable warnings for the specific quality or whatever. And you can have a few more scripts. We'll look at those too. So here's a bunch of Lua text from the main configuration file, the tundra.lua file. So in this case, this is actually the config file for Tundra itself, because it can bootstrap itself. So it actually builds on all these different architectures of platforms and tools you can see here. So it's 6 lines to define 6 explicit tool sets. So this may look like a wall of text, but actually supporting all this isn't really just typing this in. It's actually more in your code to support it, right, as I was talking about before. So this is just telling the build system, well, I've got something called Win32 MSVC, or Win64 MSVC, and that's a build tuple. And then you can use these with filtering. So the way it's set up is you can use commonality between tool sets and your targets, so you can filter on it. So for instance, you can see down the bottom that we enable O2, which is an optimization setting in the Visual Studio compiler, for all Visual Studio production releases, regardless of they're Win32 or Win64. So it's a simple Lua type problem. It fits Lua really well. You can filter it. So if you go further into the build units, the reason this is put in a separate file initially was that it uses a separate syntax. So it is still straight Lua, but you can make it look more like a configuration file, if you So this, well, the kids are all into JSON and stuff now. I don't know if you noticed. So this sort of looks like that, and it's, well, pretty easy to parse. So this is, we're building a static library, glue, for those of you who know it. Simple, single source file, you know, a CPP define. We want to tweak, add some additional compiler flags for this static library. And whenever someone uses it, that's what the propagate block is for. We want to make sure that those users of this library define the same thing. So there are many more examples in the distribution if you look at this, but this is sort of, you know, what it can look like. So moving on away from the config into the interesting stuff. So I talked about code generation. And some background, if you need it, is why we want to do this is, you know, C++ or C is rarely enough, right? Even since the 70s, we've been doing stuff like Lex or Yak, Bison, and all these tools to generate code for us that we're too lazy to write ourselves, right? And we feed them back into the build system. So you'll have a bunch of ways to generate code, basically. And the more and more, at least for myself, when I look at big code bases, I look to see, okay, so where did you generate code? What's your, you know, if it's Google protocol buffers most recently, or serialization code, you know, it almost all big code bases have this. And yeah, basically due to limitations, right? If you could write everything in common Lisp, you wouldn't need to do this, but well. So from the build system perspective, this is typically problematic. I mean, it's a simple thing to do, but it's really hard, you'll notice, to express this accurately to the build system, what you're trying to do, right? Because you get multiple sources, there are multiple things going on, and sometimes when you're trying to change the grammar, for instance, for your compiler, you'll see that it doesn't rebuild the source files correctly, or it tries to build them at the same time and stuff like that. And here's a litmus test. If you're on a project where people do make clean all the time, you're probably using a broken build system, and you're probably using code generation, and you're falling into these traps all the time, right? If clean is a magic fix, then the build system is broken. And yeah, there's some really bad examples of this. So, excuse me. So why is it then that it's so hard? So I'm going to take you through this little journey inside the build system. So say we have a configuration file, right? And that's sort of where our interaction with the build system is. But what happens internally is that this is parsed, of course. This is the first step in every build system, whether it's Make or Jam or Tundra, is to parse this description of what to do and internally create some dependency graphs, right? It's pretty simple, conceptually. So, and this is pretty much where a build system like Make ends. It does exactly what you tell it. So you'd have all, you'd have foo and mylib and a few source files, and the DAG is really, really tiny unless you start doing include scanning and stuff like that. So you can think of this as the configuration world and sort of the stuff that gets fed into the execution world. In reality, though, I mean, we don't really have these just tiny subsets of files. We really include a bunch of headers, and that's no problem usually for most build systems. I mean, Visual Studio even does it correctly sometimes, and Jam does it certainly, and you can make the Make tool do it for you as well if you're prepared to do some hacking with shell scripts and stuff. And in reality, in most build systems, this cloud of headers is usually the 90% of your DAG. It's so many files, it's so complex to update. Because have you ever looked at windows.h? I mean, come on, there's so much stuff in there, and even if on OS X, if you drag in like the framework headers or something like that, and you make the scanner look at those, man, just goes off. But up to this point, nothing's really new, right? We can do this. Here's where the trouble starts. So we're making a demo, right? And we have this awesome blah.xyz file, which is our, it's the awesome thing we generate code for. Imagine it's a custom rendering mode or whatever. It could be something fancy. We have to run this code gen binary and generate a header file of inline stuff. But you'll find if you run this naively through Jam, it'll start building foo and the code gen target at the same time. So depending on the build order and the phase of the moon, you'll you can use the previous result sometimes, or you can just have it fail, or sometimes it works. So that's, and to fix this, because it's a header, you'd have to go around to all these header files that include that header and say, oh wait, I depend on this generated header file too. Except you can't, because those are all detected by the build system itself. So you get this crazy kind of crazy situation where you can't really tell the build system what to do, right? And this is pretty common. So, and one observation then is we can't run these in parallel, right? Because we don't know enough. If you look again at the node, we can't know if we're deciding to build foo or mylib in this instance. We don't know that mylib.c includes codegen.h yet. See what I mean? So this is a dependency that's going to be discovered later by the dependency scanner. So it's easy to see why most build systems get it wrong. So the observation then to make it really, really easy is to make it just to run single-threaded. On a single thread, just execute a single command, and then you can say, before you do anything else, run the codegen. And that's what makes Jam happy, for instance. So this was one of the major things I wanted to solve with Tundra. So, but if you look at this, we can do better actually, because we know what's going on, right? We're the ones to put it there in the first place. So we can just say, don't bother with any of that stuff. Just do the codegen up first in the first pass. And then once that's done, we know that the header is updated, and then we can just run it as a regular build. So that's the basic idea behind this pass segmentation. So you'll typically have a few passes where you say codegen main pass. And it's impossible for something to leak through. And there's actually errors in Tundra that will tell you if you're doing it wrong. And we can then go wide within the pass. We can say, you know, everything we will ever need has already been generated, so just go fully wide and utilize all the cores in the machine. So to rewrite the DAG previously to this example, we see that for us to touch anything in the box to the right, we have to complete this pass. Right? And then we know that the codegen.h file is going to be on disk, and the problem is gone. So it's basically like running a bunch of multi-threaded builds after each other. So you can say that the passes are sort of your synchronization primitive on the file system. So internally, what happens is that all the nodes in one of the blocks is going to depend on something called a pass barrier. So there's actually a bunch of nodes that sit between these that all the other nodes from the next pass depend on. So whenever the last node in the codegen pass is done, all the stuff in the main pass is just blasted up onto the build queue. That's how it works internally. So here's some setup. So in this case, I'm going to make something that's usually really complex to make in other build systems. So the first thing we're going to do is we're going to compile a tool from source. So we have our generator tool, which makes some awesome source code. I'm going to compile that tool from source. That's the first thing we're going to do. And the next thing we're going to do is we're going to run that tool to make a source file. And then we're going to include it into the build. So that's 3 passes. You know, expressing something like that in Visual Studio is just, you know, you'll probably make a batch file and just run it off the side because you never could get it right. So here's something that expands a little bit in the configuration stuff we talked about before. So in this case, I'm setting up 2 passes. So I'm naming them, and I can set their build order. And you notice there's only 2 passes here. That's because if you don't say anything, you'll just get a main pass, which is always at the end. So that's where all your stuff goes by default. So if you don't say anything, it's just going to be at the end, which is convenient because that's where you want most of your stuff to be. So this is just for the other stuff. So the other piece of config we need is for a syntax extension to the Lua stuff, to inform it how to put the generator stuff into the dependency graph. I'll show you that in a minute. So we set by units, and you can see there's 2 programs. The first one is our generator. So what I'm making here is I'm telling it explicitly to use the compiled generator pass. So that means this is going to compile before everything else. It has a single source file. This is a pretty simple example. This example is actually from the Tundra distribution, so you can just check it out and play with it. So the other piece of info we need for this other program, which is the main program, this is going to include our generator file. This takes a text file and produces some source file, right? And it calls into this example generator thing, whatever that is. I'm going to show you that in the next slide. So that's how you can expose custom stuff to the Lua configuration front. And you can just name it whatever, and these functions are the functions that put stuff into your dependency graph. So without further ado, here's that thing. So this is the most Lua you'll ever write, if you need to, and you'll probably copy paste it from somewhere. So this is one of the places where it's maybe a little on the weak side. Thankfully, you don't do this a lot. So you can see that it references the pass in here. Basically, this whole function says, take this function, which I'm defining inside here, and record it as a generator of source files called example generator. You can see the name up there. And that's the thing that's going to be made available to the config scripts later. So basically, at the configuration time, we're calling this thing, and it's making a DAG node, which is a low-level primitive we're going to feed to the build engine later. You can see the call env make node. And this whole thing, this whole box here, is a closure that gets captured. So the reason this is like a function within a function is that so we can apply it multiple times, right? Because we might be building Amiga, Win32, debug, and release at the same time. So then we'd have to call this 4 times because we only produce 4 different output points, right? So with this completed, we can see that if we run this DAG, we start off by compiling our generator. So this is the first pass. So you can't really see the pass barriers in here. I mean, there's a debug mode to turn all the stuff on, but that's thousands of lines of multi-threading stuff, so this is easier to read. We then run our example generator. So this is actually going to go off to the file system and run your program to write that source file, which is then used in this pass to make the final program. So that, I mean, there's some config to it for sure, but it's on the other hand, there is a way to express these things pretty clearly. So one cool thing about this is you can actually tag programs to be for a certain architecture. So this could be an Amiga build, and we would still be able to express that the generator should build for Mac OS X in this case, because I'm running on a Mac. So there's native cross-development support in there, so you can compile your tools in previous passes for one tool set, and then go ahead and compile your Amiga or Nintendo or other crazy stuff. So to conclude on the multiple passes stuff, you can do really complex setup with them. And I think this is a sort of an enabler to start using code generation much more, because then there's no barrier anymore to get correct builds with all these stuff going on. So it makes it much easier. And they are serial. I mean, we have to wait for all the stuff in previous passes before we can complete the next pass. But if you look at it, it's not really a performance issue. It's more of a synchronization cost that you have to take if you're segmenting your build into multiple steps. And typically, we put the main bulk of the work at the end, right? You do a few coding passes, and then we compile maybe 100 files or something. All right. So let's look at some of the code. So this is a C program. It's basically portable C, pretty efficient, pretty small. A funny story is I initially prototyped this in .NET, because I thought, well, I don't know what I thought, but let's try .NET. And you know, there's Mono now and everything, and you can get it to run on every platform. So I was trying to get the best incremental build times, right? If you're trying to get the best incremental build times, you don't want random like startup delays from .NET runtimes. I was seeing delays on work class station machines to up to half a second. I mean, for many builds, if you spend half a second in Tundra, you have to send me a bug, right? Because it should worry about building. So you'll see some timings later on, but the main idea of Tundra is to like stay milliseconds within the build system, not half a second just to start it up. So loading an assembly or something was, you know, not gonna happen. So also I wanted the code to be super straightforward, like very easy. Don't use a lot of fancy data structures, just use whatever I needed and nothing more. So this of course means that you can't take your object-oriented whatever and plug it into the build engine. You can't add HTTP support or whatever, but that's it. It tries to do one thing and do it well. So the major, I guess, feature of Tundra is the multi-threading. And I can't really understand why no one does this thing before. I mean, most build systems work this way. You have a single thread that's doing all the dependency scanning work, and it's scanning all the headers, it's updating all the caches, it's doing a bunch of things, and then you can actually run jobs in parallel. But that's all great. But it only helps if you're doing a full rebuild. It doesn't help for the case where you're compiling one file, right? And I mean, speaking from experience, what I want to do is I want to compile my file, that what I'm working on, really, really quickly and make sure that everything's up to date, and I want to run the program. I don't want to wait around for the build system to do a bunch of stuff. So in reality, this just punishes the interactive stuff. And I want those to finish as soon as possible. So the default policy here is we create one build thread per CPU core. So if you have an 8 or 12 core machine, well, you get 12 build threads. So these build threads can all, you can limit that, I should say. There's some crazy stuff you can run into. Like if you're linking 12 big programs at the end, you probably don't want to run those linkers all in parallel because, well, linkers are known for allocating a gigabyte of memory and stuff like that. So you can work that around. But it's convenient to not have to type in -J12 or whatever all the time. You just know that the build system is going to utilize all the power in the machine. So what does this mean? Well, it means that rather than having one thread that can do dependency scanning for you, you'll have all the threads in your machine can do dependency scanning for you. So just to show you some numbers, here's a mid-size project, I would say. Well, in game dev, it's a really small project, but it's a mid-size. So about 100 files. 100 C files, and maybe a few hundred header files and stuff. So this is a null build, so everything was up to date, and I ran Tundra to get these timings. So the interesting part is if you look at the green numbers, Tundra spent 200 milliseconds doing implicit dependency scanning, that is scanning header files. But the program finished in 24 milliseconds. So that's the kind of scaling you can expect to see when you're using all of the machine to do dependency scanning. And actually, I had to cheat to get these numbers because normally we cache all the headers away. So the real numbers here were 60 milliseconds versus 12. Not as impressive, so we actually deleted the header cache to make it do more stuff. So I cheated a little bit. But these are the kinds of scaling you want to see when you're doing iterative builds, right? You want them to complete as soon as possible. So if you got all these threads doing stuff, maybe you've seen this in other build systems where you get the output intermingled into each other into a buffer, and you can't really tell, oh, what source file said this? What source file had this error message? You've changed the header, and maybe you build 5 or 6 files, and nothing's working, right? Well, it happened to me too. So the solution I came up with is to try to merge everything that's happening in the background into a linear output buffer. So when I'm hacking, I'm sitting with Vim, and I want everything to be nice and linear in the quick fix window so I can fix it. So the way this works in Tundra is you have one job that owns the terminal and the other ones are buffered in the background. As soon as the job that owns the TTY releases it, some other job will start buffering out its stuff and taking ownership. So yeah, it's a sequential lock basically on the terminal. I was thinking about this. I mean, it'll solve the problem, but won't it slow it down? Well, in practice, it will only slow it down if you have tons of error messages or really shifty like build programs. So I noticed it only slows down builds where I fucked up anyway. So yeah, it doesn't really matter. So I thought I mentioned about the internal build algorithm too. It's signature based. So it's similar to how SCons works, if you know how SCons works. But you basically take all the stuff that can affect your build results. So the command line, the names of things, all the input file signatures of all the files included in each build step, and you compute a signature for the node. You then compare this hash, which is an MD5 hash in my case. So you compare this to what you had on the previous build step. So that basically makes the algorithm very simple. You have to check if you have the exact same hash and you have the exact same files present on disk, you don't have to do anything. But that's the only case where you don't have to rebuild. So it's pretty robust. And the default file signing here is based on timestamps. So I produce basically hash from the timestamp. You can also configure it to do content hashing, but it's much slower. So, but yeah, you can. It's useful if you do syncing over network and stuff, and people change the timestamps for you all the time. Then it's probably a good idea. So here's what the build threads are working with. They pull work from a queue, basically, and each of these nodes are going to traverse through this state tree. So this is simplified, but you start with initial, you go to dependency scanning. From there you can say, well, I don't need to do anything. You can go to running, which can fail, of course, and you can succeed. And then you advance the dependency tree. So the one thing missing about this picture is when you have dependencies on other nodes, right, like a library or... So then there's a blocked state where you... So if you try to picture the build tree we had before, the DAG, basically the first thing we do is we put the everything node onto the build queue. We then come in and say, oh, look, the everything node has dependencies on other stuff, so we remove it, and then we blast everything up to the build queue that it depends on, right? So that scales up the parallelism even more, so we can just keep adding stuff to the queue. And the funny link from scanning to failed, I mean, how can dependency scanning fail? That's if you're depending on stuff that's going to be produced in future pass, then the build system will tell you that you're doing it wrong. You need more passes, because otherwise, this thing we talked about with the multi-thread optimizations, right? It's not going to be safe. So that's why there's a link to fail. The build queue itself is pretty easy. I've tried to take shortcuts like this in the program all the time. So if you look at the source, or if you're hacking on it, you'll see these kind of things. So because the configuration is done once, right? We have all the dependency nodes that can ever be produced, and we know the number of them. So we can just use an array. And then because stuff comes and goes on this array, we can use a ring buffer and just have a tail and a head. It's super simple. So that's one of what I mean by the advantages of keeping configuration and building really separate, because there's no way more nodes could be produced later in the build or something. We know everything up front, and only then is it possible to optimize this kind of stuff. So pre-allocations, using arrays, you'll see that a lot of stuff in the source code. So you could say it's a demo build system in that regard. Another example is memory allocation, because we're just accumulating state and then doing a build and then throwing everything away. Why worry about dynamic memory allocations? So SCons is slow in regards to this, and Jam is also slow. They spend a bunch of time allocating strings and arrays and stuff. So the approach I took was basically use a linear allocator, grab huge chunks from the OS, and just push a pointer forwards. So pretty easy, right? And once we're done, we can just blast the whole thing out. So this is one of the, well, I should say, one of the other advantages of keeping the configuration and the execution apart. So the same applies to data structures. The best possible thing is usually an array nowadays. It's so fast that it's ridiculous. So you get all this memory bandwidth, and you don't want to, spend chasing around pointers to nodes, or talking to the script side or whatever. You just want to put your data in an array and execute. So I hope there's enough of that stuff to make it really useful on multicore stuff. So basically arrays and a few hash structures, and if you look at it, that's probably what you need. Another thing, if you're making tools, don't be trapped into thinking you have to have these fancy XML formats or whatever just because someone asks for them. It would be nice with this. No, it wouldn't. Just use straight to memory files. It's worked excellent for 30 years. It still works excellent. Just make a sanity check that it's the right engine, it has the right pointer size, and then you just blast it into memory. So Tundra does this with two files, which is the header cache I talked about, and the ancestor file, which is to do signature checking. So these are written and read just straight into memory. And well, because if you have a program that runs in 24 milliseconds, you don't want to add 50 milliseconds to parse an XML file, right? It doesn't make any sense. So that's all for the technical part. I'm going to try to wrap this up then. So this sounds pretty rosy. It sounds like a pretty cool thing. But there's also some limitations, of course, or I would be a superhuman, which I'm not. So here's a full disclosure for you. The header scanning is hard-coded and fast. So if you need to scan some, if you're thinking of using this for asset builds or something, it's probably not going to do what you want. Then you have to write some C code. On the other hand, it does include scanning really fast. So the Windows version requires Vista. So if you're an XP hugger, sorry. You can fix that and submit a patch to me. And also, if you like working in IDEs, well, there's some support for Visual Studio, but it's pretty rough. And if you really need to do it today, you can do it with Makefile projects. So that begs the question, what's next? So the first thing is to reach 1.0. So this project started last summer, and yeah, it could probably come a summer release of this 1.0. There's a few bugs that need fixing, and the documentation needs improvement. And after 1.0, well, I guess IDE integration if enough people want it. As I mentioned, you can sort of use it already for Visual Studio, but it would be cool to support Xcode. It would be cool to have, this kind of wrapper generation where you can just say, oh, here's my project, make some IDE build files. So there are, the core for doing this is sort of there, but yeah, maybe we need to hack on it a bit. And some future directions too. The Lua stuff is great, but sometimes it can lead you astray because you're looking for that missing quote or you bracket, or maybe you're not familiar with Lua. So it would be great if I could, or if someone could figure out a way to pinpoint those errors, or even replace Lua with something else. So also, again, one of the advantages of having a build engine and configuration layers, you could ditch the configuration layer and do something else. Maybe adaptations to huge code bases. It would be awesome to support the change journal on Win32 because NTFS is slow, to say the least. Batching is cool. If you have a huge C++ code base, which you have for games typically, you can make it build 5 times faster by just concatenating the files in these huge lumps. Sometimes people call these Unity builds or master builds. We call them master builds at DICE. So that would be awesome to support in the build system. And currently, it's like a traditional tool, just like in Make. If you go into Make and you rename a source file, you'll see that it leaves the old object file lying around, right? Tundra is exactly the same way. It's a traditional tool. So it would be cool to support a little better cleanup and maybe keep the file system tidy. So the tool itself, it's on GitHub. There are version tags there. You can get binaries for all OSs. Oh, I shouldn't say all OSs, but I should say all OSs where binaries matter, because on Linux and FreeBSD, they're obsolete as soon as you release them, so just build it yourself. And feel free to hack on it. It's, well, this is for me who wrote the thing, but it's pretty readable, I hope. And if it's not, just bug me, and I can point you to the right area to hack. If you want to do a new feature or patches, or even if you have bugs or suggestions, just put them in there. There's a tracker on GitHub too. So one more thing, which I should mention, is that we're hiring at DICE. So just want to put this slide in there in case you're thinking about moving to Sweden or whatever. We have some pretty cool opportunities on the website right now. We're working on a pretty cool game, so give you something. So that's what I had for the prepared talk. And if there's nothing else, we can take some questions.
Is Tundra already in production use at DICE?
Excuse me. It's not used for anything important in production use yet.
So it's a personal tool right now for you.
Yeah.
Do you plan to use it in like bigger projects, like at DICE, or what's the scope?
Well, it could be definitely used there. So there's some performance that, Frostbite and game projects in general are huge nowadays. They're so big that it's ridiculous. So this tool will probably outscale anything you need for demos, and it's so fast that you really don't have to optimize any further. But for huge code bases, like I said, like game code bases, it's still a little bit unproven. So that would be a great challenge to but it's sort of my tool, so I just can't bring it into work and force everyone to use it. But we'll see.
I have a tool that generates a C and header file and from binary data. So is it possible to have a dependency on binary data? Sure. Like a bunch of images, and when one of the images changes?
Yeah.
Okay.
Absolutely. So the signature stuff just computes the signature on the file. It doesn't really care about the contents. So yeah, it's totally doable. You could set up a build that would have a single input file, which is your, I guess, texture or whatever, and you would have 2 output files, which is your C and header file. And yeah, the dependency scanner would totally pick that up. Okay. The only limitation is you can't scan the header you can't scan the image for includes. Like you can't further
No.
scan for implicit depends.
Of course.
Yeah.
And another question: have you heard the Chrome guys wrote their own new build system? I don't know how it
Oh, no,
compares.
I
They used SCons and they were totally dissatisfied because it was horribly slow, and
Yeah.
so they wrote their own thing. And I don't know, they use it already, I think, but you haven't heard of it.
Cool. Yeah, I haven't looked at it.
Because me neither. I mean, I just read it and I thought maybe you know something about it.
No, I usually follow the trends, but no, I haven't seen that one. But I'll check it out. That's a good thing. All right.
I was just wondering, how does the header scanner handle conditional includes?
Right, that's a good question. So the header scanner is just like the one in Jam, so it's optimistic. You know, so the question is, how does it handle how does the depend scanner includes with our conditional defined? So if you have one path for Windows maybe and one for Linux or one for Amiga, I don't know. So there are two schools to this. SCons does a perfect scan where it actually pre-processes the files, and which is part of why it's slow. So Jam, on the other hand, and I think most other build systems, they will just grep the source file basically and find all the includes. And Tundra does the latter. It will just scan everything. So if you think about it, the only bad thing you can get from that is you get a more restrictive dependency graph, right? So you'll depend on more header files even though you're not really using them. That's going to be your end outcome. It's still going to find all the files. It's just not going to, you can sometimes you can get a rebuild on Mac because you changed the Windows header file. So, but that's about the extent of it. So it behaves like Jam in that regard. All right. Thank you for coming.